So, good evening, everyone. So, we will be conducting the week one live session of the Computational Fluid Mechanics, Fluid Dynamics course. Okay. And I will be your TA for this particular live session. So, this live session will be conducted weekly at the same time. We will have the same link. And uh,
Sir, please, sir, echo coming, sir. Echo sound, sir. Like rebounding.
okay.
Okay means three times coming like. Okay, like this.
So someone is asking, will we get the recording of this session? The answer is yes. The recording of this session will be made available to you. If the echoes is still persist, let me check in the like whether in the recording the echo is coming or not. If it is there in the recording also, then I have to like, sort it out. Okay, okay, good to know. All right. So I want to ask, mm, I want to ask you guys one thing. Like, what is the background for most of you? So, how many of you are like doing your bachelor's here, bachelor degree program? So, like, I am asking this to know the like background of the audience. All right, I can see a lot of hands. Okay, that's good. You can lower your hand and master student. So how many of you are a master student? Okay, okay, okay. You can see a few. Harshini. Okay, all right. And what is the background for the like rest of you? Is there are you guys like research scholar, working professionals? I would like to know the background and why you have taken up the course of CFT. What you are expecting from the course of CFT. So someone wants to like say they can unmute themselves and like
Good evening, sir.
yes,
This
good
is
evening.
Dr. Sagar Mane Deshmukh from Tolani Maritime Institute. It is in Pune.
Okay,
So we are actually Maritime Institute. We did not have computational fluid dynamics subject earlier in the entire curriculum of marine engineering.
okay, okay,
So we are affiliated to Indian Maritime University, and recently, for the first time in revised pattern or syllabus 2021, they have introduced this subject, Introduction to CFD.
okay.
When I was in the other
Sir,
university,
please check, sir. I am unable to hear, sir, because echo sound coming, sir.
Okay, uh, Basant, right?
Yes, sir. Yes.
Yeah. So, like, I would request you to means check in your audio system as well. If you are joining from two devices, I can see your name twice. Maybe like it's echoing from the the devices itself because like others are not reporting this issue. Okay, would request you to please check your audio system.
Again, I will join, sir. I will
Okay,
leave
sure.
and join, sir.
Yes, yes, please. Okay. Is Dr. Sagar, you might continue.
yes. So as this is introduced for the first time in our curriculum,
Yes.
I I have to teach this subject. I have started learning this,
Okay.
but still I want to hear it from your side also, so that
Mm.
some additional knowledge I can gain from your sessions.
Okay. Okay. Yes, thank you for like joining. Uh, hopefully this will be productive. Uh, okay.
Yeah, sure. Thank you, sir.
Yes.
Good.
Thank you. So like anyone else?
Yes, sir. Now, okay, sir. Now, okay.
Okay. Okay. That's
Okay,
good
thank
to
you.
know. All right. Yeah. So like hopefully, like all of you are familiar with the concepts of fluid mechanics. But like since it's a CFD course, like we will be solving the fluid mechanics like equations or like transport phenomena equations um in a like numerical frameworks. So the basic knowledge of fluid mechanics is thus required for doing this like course, and we will uh, like do some revisions of that. And then like proceed. Okay. Uh, so all of you have done a basic fluid mechanics course here. Is there anyone who has like not done a fluid mechanics course before this? Okay. Like Harshini, have you like done a fluid mechanics course?
I've done a basic mechanics course. I've not really done specific to fluid mechanics. I'm from a physics background.
Okay, okay. So you are from physics background. So you
Yeah,
have you done anything like continuum related transport phenomena, any such courses?
not exactly. So it's been
Okay,
introduced very little somewhere or the other, but not into the crux of it. Yeah.
okay, okay. So there will be a basic recap of the like the equations that we are going to solve, because we since it's a CFD course, we must know the equations that we are going to solve. Like in this course. So that's where the fluid mechanics part of it comes. So we will do some recapitulation. So one thing that mm, yeah, can you see the pen marks?
Yes, sir.
Yeah.
Yes, sir. Yes, sir.
Okay, okay, okay. Mhm. That is yeah. So one thing that is in this fluid mechanics that we have, it's the first thing that we should know is that this is generally like solved from an Eulerian perspective. So those who have done fluid mechanics course, like someone may like please say what do you what do you understand if someone says it is like based on an Eulerian perspective, uh, like in contrast to a Lagrangian framework. So if someone says it's done on a Eulerian framework, what will you understand? Can someone please answer? Okay. Yeah,
Sir, excuse me, sir. After
yes,
class, can I get the notes and all? These notes will be right, sir.
yes. This will be available to you. The slides and the recording will be available.
Okay, sir.
Okay.
Thank you, sir.
If any like anyone who has done the uh, fluid mechanics course, can anyone please share what do you understand by Eulerian framework?
Yes, sir.
Yes, please.
Framework he deals with the fluid mechanics, with the fluid. That the fluid is flowing in whatever we are going to analyze. The analysis is based on the space region.
Hmm.
So the individual particle will not be observed. So in
Yes, that is correct.
Lagrangian, we deal with the single particle.
Yes. Hmm. So that is absolutely correct. So basically, in Eulerian framework, what we do, we have a like region in the space which we are observing. As the fluid particles move in and move out of the system, we are observing this, and in this like stationary a global coordinate system, the like equations are represented. Unlike Lagrangian framework, which actually focuses on just one particle and what is happening to that particle. Now, the challenge in this Eulerian framework is that our like basic dynamic equations, like if you consider the Newton's law of motion, like F is equal to ma. Hmm. So that is from a Lagrangian perspective. So m is the mass of the particle, and force is F is the force acting on it. A is the acceleration. The same thing. What we have to do here in the Eulerian, we have to convert it into the Eulerian like framework. So for that, one concept that is very important. is material derivative. So one concept that we use very often is called material derivative. So let me go to this. Yeah. So if the first question is that we will be doing here is this, that like the total or material derivative that combines the effect of position and time on a flow variable is given by what? So it is asking basically what is the material derivative. We will represent it. Hmm. So suppose you have an Eulerian framework, you will basically write your force. This is equal to mass of the particle into dt. Right. Hmm. So yeah, someone is trying to join. Okay, yes. So like this will be the representation. So similarly, in this in a Eulerian framework, we can also use the same thing. So since it is like in a region of space, we will use the density rho, and we will use the material derivative. Hmm. So material derivative is basically to convert the partial derivatives we use in a Eulerian framework to this kind of a derivative which we can use in Newton's equations. So this will be equal to force. So let me represent it by small f, so that this is basically force per unit uh, unit volume. So this is since here also mass per
Sir,
unit volume.
please,
Yes.
please, sir, the second equation I'm not getting, sir, second equation.
Okay.
Go
Okay.
on.
No problem. So basically, like this only, the I am writing it in terms of like per unit volume in a Eulerian framework. Hmm. So this is your mass density, right? Mass density. So this is mass per unit volume, and this is basically our acceleration term, dv/dt. Here, instead of this is Eulerian, and this is Lagrange. So here, instead of writing just this small d, we are writing this capital D to basically differentiate the normal Eulerian derivative. Because if you have a derivative with respect to space, that is not for that particular particle. And if you have a derivative with respect to time, this is like for a point in space, right? It's a Eulerian framework, so it is for a point in space rather than a fluid particle. So what we want to actually solve is for fluid particles, like the actual mass of the fluid. So that's why what we use is a concept called total derivative. So this is equal to some force per unit volume. So you may be more familiar with this kind of a notation. This plus you might have the velocity. I'm writing v. So I'll write v here. So this you might be more familiar with. So this is the pressure term. This is the viscous term. So these are basically forces, different kind of forces that are acting on the fluid at this particular point. So this is how Eulerian framework is
That's sir,
basically
mu bracket start this equation.
expression.
Yes, sir.
Okay. I'll
Minus del.
write it more clearly.
Yes.
Yeah. So here mu is the viscosity. So this is basically the viscous force that I'm writing. Grad V plus this is the transpose V. So this is the Navier-Stokes equation. You might be familiar. So if we do this Stokes assumption, everything we take, we will arrive at this particular equation. This is the Navier-Stokes equation. Momentum part of the Navier-Stokes equation. Okay. So the question here is, what is dV? How is this ddt, this derivative, how is it represented? There are four options. Okay. So this is directly from the fluid mechanics. So in fluid mechanics, this part will be covered. The difference between this Lagrangian and Eulerian, is it clear to all, or like if there are any questions, you may please you are feel free to ask.
So that is capital D. This is the capital D. This is the small d. So, okay, capital D
Yes,
represents
capital D is the this total or material derivative. So basically, here what is happening is in Eulerian framework, we are focusing on a space. Okay, here what we were doing, we are focusing on a particle. So this particle, on this particle, some force F is acting. Hmm. And we are like calculating the velocity, acceleration, everything we are calculating for this particular particle. Here what we are doing, we are focusing on this space. So here some particles will come and then go out. Hmm. Like many things can happen inside this. Whatever particles are coming, they are experiencing some kind of force, and like from there only we have to like uh, try to calculate the velocity. Hmm. So to represent this, we are using capital D dVdt. In the Eulerian framework. We use this material derivative to represent this acceleration. So dVdt, this small d, in Lagrangian framework, dVdt represents what? Acceleration. Here, capital dVdt, this represents acceleration. So it has two components. So this part, it has two components. This particular part, this has two components. So one is the special derivative. This is there. Here also, this is there. Like ddt. So time derivative. Time derivative obviously will be there. How in this particular space, how fast your with respect to time, how fast the velocity changes. So that is one part of the acceleration. But here, in the Eulerian framework, there is also another part. What is that? That is how fast, like from this small volume area, from the small volume, particles are leaving and particles are entering this system. So that also we have to calculate. Otherwise we will be missing out on a like acceleration term, since not all particles are staying inside this like small volume. Some particles are leaving and some particles are coming inside, so we have to also account for that, and that is done with this term. Okay, so this is like gradient operator and this is velocity. So v dot grad. So this is what is like represented by material density. Uh, if you have done fluid mechanics course, this must be clear to you. But like, if there is any doubt, I can like explain in a more elaborate way, which might help you. So, what would you prefer? Is this clear to you?
Yes, sir.
Okay. Okay.
Yes, sir.
So let me proceed. So yes, so this is the correct option for the material derivative. This represents like means the if we do operate this on velocity, this will represent the acceleration. If we operate it on some other transport variable, then also like it will like represent how that particular term is like changing for the material. So this is,
Hello, sir.
yes, yes, please.
May I interrupt you for some time?
Yes, yes, sure.
Uh, Sir, in this equation,
Hmm.
the extreme right term v cap dot grad.
Okay.
Uh,
In
so
the
what?
previous slide. Okay.
No, no, the same which you are
Okay. Okay.
explaining.
All right. All right. Yes.
Take a B option. That which one is
Yes.
correct?
Yes. Yes.
So basically, that is a convective derivative, right?
That is
V
correct.
cap dot
Yes.
grad.
This is a convective data.
I'm sometimes confused with this V cap grad. I mean V cap dot grad and grad dot V cap. So what is the difference between these two?
Okay. Yes. Sure. So this is basically an operator. So if I write ddt, this is not a complete thing, right? Only if it
Correct.
acts on a function, then like it has some meaning. Otherwise, this is not a complete thing. So what is this? This is called an operator. Hmm. So similarly, this v dot grad. So what is grad? Grad is basically, if I write in 2D, this is del del x I cap plus del del y j cap, right? So
Right.
this is an operator. Grad is an operator, right? Because it has no meaning, but only if I like perform, since these are derivatives, right? These are derivatives not acting on any function right now. Only if I put a function here, then it has now a meaning. So this is now del del x of f I cap plus del del y of f j cap. Now I can evaluate this. I can have a value from here. Otherwise, this is just an operator. So similarly, if you have v dot grad, this is actually an operator. This is basically, uh, let me write it like this: vj cap. This is suppose the velocity dot product with del del x I cap plus del del y j cap. So if I perform this dot product, what will it will be? Del del x plus v del del y. But this is not a value. This is just an operator. Only if it acts on a function, then I will get some value out of it. Otherwise, I will not. However, what you are asking about is grad.v. Grad.v is not an operator. It is, this is like acting. Yes, someone is trying to enter. Okay. So here, this grad operator is acting on v. So how I can evaluate this? This is del del x I cap plus del del y j cap dot u I cap plus v j cap. Now, if I perform this particular dot product, I am operating this del del x will operate on u. Then it will become del u del x. This is a value. This is not an operator. And similarly, del del y will operate on v and will give me this del v del y. This is also a value. This is not an operator. Okay. Is the difference between these two clear?
Yes, sir. Thank you.
Okay. So if there is any other question, please ask. Okay. I'm going to the next question. So this is also for like from fluid mechanics itself. So this is continuity equation. So this is mass continuity. Like basically, this statement of mass cannot be like created or destroyed. This is the mathematical form of it. And for incompressible flow, this becomes this. This is simplified to this form. So from this information, which of the following statements is correct? So can anyone like say?
Sir, B correct, I guess.
Yes, B will is correct. So basically, this is dependent on the previous problem itself. If we know what is material derivative. Hmm. So incompressible basically means the material's density cannot change. Hmm. So if the material's density cannot change, what will happen? The material derivative of rho will be zero. So that's one of like way of to think about it, and also we can like do it very directly as well. So this can be also written as del uh, t of rho plus this is multiplication of two functions and by a derivative operator. So this will be rho dot grad dot b plus v dot grad rho. So if I combine this first term with the second term, this will give me the material derivative. So this gives me del rho del t, d rho dt plus rho grad dot. Now it is given in this question that for incompressible flow, grad dot v is equal to 0. So this can be taken as 0. Like immediately we get d rho dt is equal to 0. Okay.
Sir, incompressible flow implies that density also constant, no, sir? First point.
Yes, density is so density material. So for a particular material, for a particular fluid particle, the density is constant. So the
Yes, sir.
concept is like that. So what else can happen is that your like in a flow, especially you might have so density might be a function of x or the like the space. So there might be different density at different location, but like if the material derivative remains constant, then still your flow is incompressible. So it is not necessarily true that your density, that rho, must be constant. If rho is constant, then it is incompressible. But for incompressible, we do not exactly need rho to be constant. What we need is this condition: d rho dt. This should be zero. So if I like expand this, I have del t of rho plus v dot grad rho. So if this term cancels out this term, then also it is incompressible.
Sir, dou rho by dou t
Hmm.
plus v grad rho is equal to 0, sir. Kindly, sir, explain this equation.
So this is basically an expansion of this material derivative. We have learned the expansion of material derivative in the previous question itself. So
Yes.
this is the expansion of material derivative. So simply I am just using this to expand. Okay.
Sure.
So del t is operating on rho, and again v dot grad is also operating on rho. So
Sure.
addition of this is 0. So if these two terms cancel each other, then also it is incompressible. Need not be rho is constant. If rho is constant, you can see like both of these terms are 0. That is a trivial solution. But other solutions may also exist. Okay. Okay. Is there any doubt?
No, sir.
All right. Okay. Yeah. So we did this. Let's go to the next question. So here two statements are given. Three statements are given, and we have to choose the correct statements. So you can like read the questions. So two momentum equations are given basically, like one and two, and uh, like three is given. Like it is describing Navier's equation. So which one is Navier's equation? That is the question. So can someone tell me which one is the Navier's equation?
Equation 1.
Equation 1 is the Navier's equation. Right? So this first left hand side, and this is same for both, and this is nothing but this like rho del del du. Okay. So it's written in the index notation. I will write it as well. Then there is like this rho PB is there. So this is the body force. And uh, for the Navier's equation, we will write the stress. So the whole complete stress is given. So in this case, this second equation is what? The second equation, the pressure is taken out, and this is not the complete stress. This is the deviatoric stress. So these concepts are there in the in like fluid mechanics. So if if you take the stress, so stress is a tensor, right? It can be represented in a matrix form, like it can be decomposed into a matrix form, like given a set of coordinates. Hmm. So whatever, suppose you get the like values of the like matrix, you take the diagonal terms and add them up. Hmm. So that is the trace. This is called the trace of the stress tensor, and divided with by 3. So whatever this mean, like mean of the trace that you get, this can be represented with pressure. So if that is taken out, then this is called the deviatory stress. So this is called deviatory stress, and this is the total stress. So Navier's equation deals with the total stress, and thus the first equation is correct. And is the third statement correct? These three. Statement 3 is also correct, because here we have not really used any assumption at all about what the fluid might be. In fact, we have not used the assumption that it is a fluid. Yeah, so the like this equation is basically just says that the velocity that is dependent on your like stress, and that can be for like anything. So it does not really say anything about the nature of the fluid. It is independent of the nature of the fluid. So which one is the correct option? The option
A.
A. Option A is the correct option. If there is any question, please feel free to interrupt me and ask. Okay. Let's do another question from like this topic itself. Now what we are doing is we are decomposing the stress. Hmm. So if we take a Newtonian fluid, so the fluid that we are going to take here is like Newtonian, homogeneous, and isotropic. So if these three assumptions are taken, then what will be my stress tensor? What will be my what my stress tensor will look like? So one thing is very sure is the pressure will be there, and the pressure is always like taken as this negative. Hmm. So here, like I said about the stress, so this is basically minus of this is taken as pressure. Hmm. So this is called also called the like hydrodynamic uh, pressure. So this term will be there. Minus P delta Ij will be there. So option A and C, B and D are incorrect. So what else is there? Can someone say? So
It
for
is A, A is given actually on slide. We can see that.
oh,
But
okay,
how
okay.
the
I skipped the slide. Yeah. Okay. Yeah. Tell me.
how is the two coming in the equation one side?
Okay.
Yes.
Okay. Yeah. Uh, sure. So basically this like two is actually from like definition. So this part. So this is like the deviatory stress tensor. Hmm. Uh, outside the pressure, like if we take the pressure aside, the rest of the stress, this is basically in Newtonian fluid. What we assume is like c a constant into the uh, velocity. So this is the velocity gradient, and so two velocity gradient is a second order tensor, and the deviatoric stress is also second order tensor. Only these two can only be like generically related if we issue a fourth order tensor as a like relation term. But you don't like we don't have to like get into this right now. So if I like take these assumptions of homogeneous and isotropic, then I can actually simplify this a lot. So this is Newtonian. So this is Newtonian. This is the generic Newtonian expression. So if I like put the homogeneous and isotropic assumptions, then I can simply like simplify this and like write it as some lambda, hmm, and like this is the trace of the trace of the velocity gradient, and uh, yeah. So since this is a second order tensor, I have to multiply a Kronecker delta plus another constant which we take as 2 mean. And the reason we do this is like if you put this in the momentum equation, you'll see these two cancels out with a like half. Sorry, I think I have like missed out a little. Yeah, okay, sorry. Uh, yeah, these are like E. These are taken as E. Uh, Yes. So here E is given actually. E is given. So this E is represented like this. This is the given expression is this, and here we can simply write it like this. Hmm. And this 2 is basically given so that like it cancels with the half. So it's a constant, and we take this 2 so that like we have a very like nice looking like expression. And also means if we solve the like momentum equation for some uh, classical cases like for parallel plate channel and all, this this mu, this has a very important role in it, and this is basically the viscosity. So that's what comes out in the momentum equation when we take another assumption which is also known as the Stokes assumption. So if we take the Stokes assumption, like this part will not be there anymore, and only the mu part comes out in the equation, and you will have the momentum equation like I think I wrote it here. Momentum equation like this. So here only the this means the coefficient is mu. It is not 2 mu. It is the 2 has been cancelled out with this part, and this is nothing but the EI. Okay.
Right. Thank you.
Okay. Okay. Thank you. Hello.
Homogeneous part given homogeneous part, which one homogeneous part, sir?
Uh,
That
uh,
the Newtonian homogeneous and isotopic is given.
yes. So
Homogeneous,
okay.
sir.
Yeah. So isotropic means it is like independent of direction. So all these the constants, this mu and lambda, these are not dependent on any direction. Hmm. Uh, so for that case, like means yeah, these are like means these are simply constants independent of any direction. So no direction x y z, no direction is special in this case. And homogeneous, what does homogeneous mean? Homogeneous means like throughout the fluid volume, it is like not changing. So these are constants. So these are not functions of x and y. This lambda and mu, these two constants, they are not functions of x and y. So that is basically the meaning of this homogeneous and isotropic. Okay, all right. Okay, so the next question is like the Euler's equation of motion. So Euler's equation of motion is basically when we yeah, assume the flow to be inviscid. So that means there is no component of viscous force involved. Hmm. So in the all the options, basically the viscous force term is missing, as you can see. So you have to just simply identify the correct momentum equation. So can you identify the correct momentum equation for this? Four. So there are two places of variations here. One is in the this material derivative term. So some equations have this plus sign and some equations have this minus sign. So which one is correct?
Plus sign.
Yes. And in the pressure, some equations have this minus and some equations have this plus. So which one is correct?
Minus.
Minus.
Yes. Yes. So uh, option
Option
B
B.
here is correct. Yeah. Okay. Like another question for the mechanics portion. So this is about streamlines. Yeah, this is about streamlines. So three statements are given.
Sir,
So yes,
please, sir, the previous slide explain, sir.
yes, definitely.
Uh,
Uh,
V by root OT
mhm.
plus V grad.
Yeah, what is your question?
Sir, explain this equation again, sir.
Okay. So this is basically the momentum equation. So this is the total derivative term that we have discussed. Hmm. So this is rho dvdt,
Sir,
and these are the forces. This is because of the pressure gradient. Hmm. So this is there, and this is the body force. This is
sir.
any body force, gravity. It might be some other forces. It might be. So this is the body force.
Okay, sir.
Okay. Yes. All right. So here, yeah, three statements are there. The first statement is streamline is an imaginary line such that tangent to it at any point gives velocity of the flow at that point. Is this statement correct?
Yes, sir.
Yes, this is correct. So streamline is basically like the definition of streamline is that every point on this line like will is the tangent to it will give us the direction of the velocity. That is the definition. Okay. Second statement is two streamlines in a flow field never intersect. Is this correct?
Correct.
Yes, sir. Correct.
Yes. They can never intersect. Why? Because at the intersection point you will have two tangents, and no, you can never have two different directions of velocity at a particular point at any instant. So two streamlines can never intersect. Okay. Next statement is streamlines in a flow field may intersect to form what is known as a flow net. Is this correct?
Incorrect.
This is not correct because, like we just now discussed, streamlines can never intersect. Okay, that is good. So option C here is correct. All right. Yeah. So this is basically the equations that we will focus on. Every means equation that we will try to solve in this whole course will have this kind of a form. So this is like the form is known as general form of conservation equation. Okay. So it might be momentum conservation like we have like so far discussed, like the Navier-Stokes equation. It might also be some species conservation equation, or like the energy conservation equation using your temperature. So a lot of such conservation equations might be there. So what is the general form of it? So out of these four, which one is the general form of conservation equation? That is asked. So can you tell me?
Option B.
Option
B.
option B. Yeah, that is correct. Hmm. So option B is basically, where is the pen? Yeah, option B is basically the equation which we will be solving. So phi here is the the variable. So it might be velocity, it might be density, it might be like concentration of some species, it might also be temperature. So this is basically the general form of equation. So here are four terms. So can you like tell the name of each fourth term? So these are very important terms. So this is the transient term. Hmm. So this is the time derivative. If anything changes with time, then this term will be important. This is the convective term. So this is like basically tells us the change of this variable phi, which is associated with the velocity of the flow field. Hmm. So this is the convective term. And a very important term is the diffusive term. So this is the diffusive term, where this gamma is diffusion coefficient. So in the momentum equation, this diffusive term is the viscous term. So how the momentum diffuses. So like from a high concentration of like uh, to a low concentration, there will be some diffusion, and that is basically represented by this particular term. This is, and this is source term. So this depends on this is different from problem to problem. If there is a external pressure gradient supplied, then like the pressure gradient term will be there in the momentum equation. For example, in the thermal, like the temperature equation, in the energy conservation equation, if there is a heat source, something which is supplying heat, so then that will come here. And for example, in species transport equation, if there is some reaction going on, some species is being generated or some species is being consumed due to certain reaction, then that will be represented using this source term. Okay, all right. All right, so we will start with the like uh, types of partial differential equation, which is like directly related to the course. Uh, so we can take a 2 minutes break and then like we can resume. Okay. Is that okay?
Yes, sir.
Yeah. All right. Hello.
Sir.
Yes.
Yes.
So uh, can we resume?
Yes.
Yes.
Yes, sir.
Okay. Okay. Yes. So yeah. So what we will do is we have already seen like the main type of equation that we are going to solve. It is this, like the conservation equation. And first thing that you can notice here is these terms. These are like the partial derivative terms. Del rho del t. Then this grad is there, which is the spatial partial derivative, as we have already discussed. So this kind of terms are there. So these are in general partial derivative equations. Hmm, Okay, and also like we have to like for that reason we need some kind of a classification and to see how we can solve this partial differential equations. And also like all of these equations are not linear in nature. What we mean by linear? Like linear when the like different means the main variable they are like multiplied with each other. For example, if you see the momentum equation, in the momentum equation, yeah, so in the momentum equation, this particular term is there. This is the convective term. Here, u and u is multiplied like with the derivative of u. So the the unknown variables, the derivative of the unknown variable is multiplied with the unknown variable. This particular term makes this a non-linear equation. So we have to also accommodate for the non-linear equations, and we have to like develop a structure in which we can solve this kind of equation. And also there is another thing that these are all like these conservative equations, these are second order. So these are not first order equations. So first order, if the partial derivative is like the highest order partial derivative is like of the order one, like this del del t. If this were the highest order derivative, then this would have been a first order equation. However, exists a higher order derivative where in this term. This is the diffusive term. In this term, we have this del x with this gamma del phi del x. So this is the second order derivative. So because of this second order derivative existing, our general form of the conservation equation is a second order partial differential equation, and we have to like try to see what are the different types of such equations. Hmm. So let's come to the linear type. Okay, so let's first write down a like a linear uh, partial second order partial differential equation. So, so these are there in the first week lectures, uh, week one lectures. You will find all these content. So what are the subscript? Subscript basically I am like uh, this is basically nothing but del square phi. So the derivatives I am representing using the subscript. Okay, so this is there, and like this can be this is equal to some function which is a function of all this x, y, and phi, like everything can be there, yeah, and also like this phi x and phi y, which are the first order derivatives. These things can also be included. Hmm. So what matters is basically the like the highest order terms. So A, B, C, if these are A, B, C, if these are constants, then this particular form is known as linear equation. Okay. Now, what about semi-linear equations? So semi-linear equation, in semi-linear equation, we can have this as functions of x and y. So if these are functions of x and y, then these are called semi-linear equations. Okay. And this function is there. This function is there. These contains like phi x and phi y functions are also in there. So this is semi-linear equation. And this linear and semi-linear equation we can like tackle very easily using um, using different kind of methods that we will subsequently learn. And another form is the quasi-linear equation. So in the quasi-linear equation, we will also have phi, hmm, phi terms there. Hmm. So also phi terms will be there. So these are a little difficult to solve. So these are quasi-linear equations. Okay. So linear we will have constant coefficients. Semi-linear we will have functions of x, y, and quasi-linear we can also have the unknown variable in the coefficients of the highest order derivative. However, we cannot have two highest order derivative multiplying with each other. Those are not like neither linear, semi-linear, or quasi-linear. They are completely non-linear equations. So those equations we are not focusing on. We are only focusing on these three types of equations. Okay. So another one very important concept of this uh, second order partial differential equations is the
Sir, please,
yes.
please, sir, explain that previous slide because my network not there, sir.
Okay, okay.
Sir, yes.
Yes, yes. All right. So, basically, this is the like equation. So A, B, C. If these are constants, then this is a linear equation. If these are functions of x and y, then these are semi-linear equations. And if these are uh, a function, the A, B, and C, these coefficients, if these include phi as well, then this is a quasi-linear.
Sir, why are telling semi-linear, sir? Semi-linear.
Uh,
Sir, explain semi-linear, sir.
Yes, so semi-linear basically like if the coefficient has if the coefficients here are not constants.
Oh, okay.
Okay,
Okay, sir.
all right.
Quasi means quasi-linear, that is XY phi, sir.
Yes, yes,
Quasi-linear.
yes. Okay. So the unknown variable is also part of the coefficients.
Okay.
All right. So yeah. So the uh, next part we will do the characteristics of a PDE. So like yeah. So there is a means very important concept here in partial differential equations, which is characteristics. So here we are like let's take this general equation that we had taken previously. Hmm. Xy plus c by y1. So this is equal to some function. So here, one thing is there, like to have a second order partial derivative, what we must have? We must have a very smooth function phi. Phi must be smooth everywhere in the domain, right? Otherwise, we will not be able to take derivative. Hmm. So if we are not able to take derivative, uh, then the second order derivative will not even be defined. Not only phi, we must also have the first order derivatives phi x and phi y. These should be smooth everywhere. Otherwise, my phi xx or phi xy, like phi yy, these derivatives will not be defined. Okay. Hmm. But however, there can be some curves or lines along which these derivatives, this phi xx, phi xy, and phi yy, these derivatives are discontinuous. These might be discontinuous, and those curves, those uh, paths are called the characteristics of a PDE. Okay, so if it is means uh, yeah, so this can be found out in the following way. Hmm. So uh, let's yeah, let's try to see when this can be this phi xx, phi y, xy, and this second order partial derivatives. This when this may be discontinuous. So we have let's write it in a linear equation. So this is one equation. Another equation that we can actually have is if I have phi xx dx plus phi xy dy. What can I write this as? So this is a second order derivative of x, hmm. and like phi xy dy. So what can this be written as?
Del square phi by dx square into dx.
Phi x.
Yes. Hmm. So this can be written as phi x. Uh, let me try to. So this is basically nothing but del x of phi x dx plus del y of phi x dy. Hmm. This portion. Okay. So this becomes phi x. All right. Is this clear? Is d phi x is the differential of this phi x. Sorry. Right. If total differential of phi x is taken, it will come in this form. Is this clear? This how I arrived at this. So this portion is nothing but phi xx. This portion is nothing but phi xy. Hmm. So if I multiply this dx and dy with phi xx and phi xy, I will get d phi x. And similarly, I will have if I take phi xy dx plus phi yy dy, I will have d phi y. Hmm. So what I will do right now is take this equation, hmm, this equation, and this equation. Yeah, tell me.
Sir, how it came, sir, d phi y, sir? Phi xy dx plus phi yy dy. How it
Hmm.
came, sir, d phi y?
So what is phi xy? Phi xy, I can also write phi xy as del x of phi y, right? Phi xy.
Yeah.
I can write
Yeah.
like this. Hmm. So this is dx plus this portion phi yy. How can I write? I can write as del y of phi y dy.
Sir.
So this is the how the total derivative is written. So this is the total derivative of d phi. Okay. So if I represent this equation, so this becomes a b c. Here is phi xx, phi yy, phi xy, and this is equal to. So the first term will be f. This is the equation one. So and second term here dx dy 0, and this will be d phi x. And similarly here 0 dx dy, this is phi. Okay, is this clear till now?
Yes, sir.
Okay. Hmm. So now, if I want to have like discontinuous like second order derivatives, what should I do? I should make the determinant of this coefficient matrix 0, right? Hmm. So this ABC dx dy 0, 0 dx dy. So what will this be? This will be a dy square plus b. This will be minus, right? Please let me know if I am doing correct. This is equal to 0. Hmm. Okay. So this can simply be written, rearranged like this. Okay. So you can see we got an like a quadratic kind of an equation. Now this is a quadratic equation only like if a, b, c are constants, we can easily find out the values of dy dx. Otherwise also we can, but like if we will get constant values for dy dx if a, b, c are constant. So if I have a, b, c constant, what does it mean? It means I have a linear equation. So for linear equations and also for like other equations as well, like dy dx, I can simply use my rule, Sridharacharya rule. So this plus minus v square minus 4ac. Okay, yeah, is this correct?
Yes.
Okay. So what have I done? Like I have done a lot of maths, but what exactly I have done? So I have taken this equation. This is my primary equation, this first one, and what I have said that I have some like special curves which are called the characteristics of the PDE, and I will like have them. Wait, someone is trying to join. Okay. So I will have like the discontinuous of the second order of PDE. So for that I took the total derivative of phi x and total derivative of phi y, and I am like saying in which case these phi x x, phi y y, phi x y might not have like unique solutions. So like it will give me the discontinuities of it. So I put the determinant equal to 0 and I got this equation. Now this equation, what will this equation give me? This equation will give me some kind of a line or a curve in my xy plane. So in the domain, basically, the domain where I am trying to solve this partial differential equation. And what this like lines will represent? Will represent where the partial derivative, second order partial derivatives will become discontinuous. And this will play a very important role in determining the nature of the PDE and also like how we will approach to solve this numerically. So that's what we will see. So here you can already see like whenever you have this kind of quadratic thing, this determinant term comes, and this determines the nature of the solution, right? So if b square minus 4ac, this is greater than 0, what I will have? I will have two real roots of this equation, right? And what about if this is equal to 0? Then I will have one root, right? Unique one root. So, and what about if this is less than 0? Then how many unique roots I will have? 0, right?
0.
Real roots I will have 0. And this like basically based on this classification, we can divide this second order partial equations, especially the linear ones. Like for the semi-linear, we can like try and develop some regions where this falls under category 1 or 2 or 3. But for linear equations, we will get a very clear cut picture that what kind of an equation this is. Like, is b square minus 4ac is greater or equal to 0 or less than 0? Okay, so okay, so let's do a question first. So what is the nature of real characteristics of the following equation? So the equation is given, and like we can definitely like memorize this particular uh, equation. So this particular equation we can memorize. That will help us figure this out quickly. So here a is 1. So I will simply means write this square, and this is minus b, so minus 6 dy dx plus 4, this is equal to 0. So can you find dy dx? So this how much this will be? Can someone calculate?
Yes, sir. A is equal to 1, B is equal to minus 6, C is equal to 4. So B square minus 4 is by 2, and you can do like this, sir. But sir, from the first equation, how it is coming, sir? From first equation, dou square theta by dou square plus like this given.
Yes.
But
So this
second
is
equation,
given.
how? So
Yes.
how it is coming? This equation,
Yeah,
how it comes?
that's what we discussed so far. So first equation, like the given equation, is this basically. So
Okay.
from here, what we are writing is this. Okay. So this we can memorize. This will give us the characteristics. So if the given equation is this, the characteristics will be given by this equation, and that's what we are doing. So here, like if I compare it with this form, if I compare it with this form, A is coming out to be 1, B is coming out to be 6.
Minus
And
6.
why
Minus 6.
minus 6? This is
Sir,
plus 6 only.
no, here, sir, minus 6 is there, no? If you governing equation plus, then it automatically will be minus, no, sir?
So in this characteristic equation, this is
Okay,
coming.
okay, yeah, yeah,
Okay,
okay, okay.
okay. Here this is minus sign is there. So here this plus
So,
sign is there. Okay. So B is plus 6, C is 4, and from there I got this equation. Okay, is that clear?
okay.
Now we have to solve for dy dx. Dy dx is basically a variable, and this is the quadratic equation. So I can simply put my Sridhar formula and find this out. 6 plus minus b square, which will be 36, minus 4ac. So that will be 16. divided by 2. So this will be 1, sorry, this will be 3, this will be 3 plus minus root 5. So 20 is there, so 4 I can take out, and like 2 will cancel, so 3 plus minus 5. So what are these? So dy dx is this. So dy dx, if it is this, like let me say this is m. So if dy dx is equal to m, I can find out the equation of the characteristic. What this will be? Y is equal to mx plus some constant of integration c. What is this an equation of? This is an equation of straight line. There will be two straight lines because I have two values of m. One is 3 plus root 5 and one is 3 minus root 5. So I have two values of m that will give me two straight lines. So there are two straight lines along which the second order partial derivatives of this particular equation is discontinuous. Okay, so those are the characteristics. And what is the question? The question is nature of the real characteristics. So the characteristics we have found, this is the equation of the characteristics. So this is a linear equation. We have found out dy dx is constant. That means the characteristics is linear. If we had found that dy dx is some function of xy, then it will be of a different form. The curve will be differently shaped. But here this is shaped like a straight line. So the correct answer is A. A. Yeah. Okay. Is the concept clear?
Yes, sir.
Okay. So yeah. So yeah, basically, so far what we have done is like we have not named the classification. So if b square minus 4ac is less than 0, it is called an elliptic equation. Okay. So like means we have said that there will be three different classifications. If it is less than 0, it is called an elliptic equation. What does this mean? This means that there are zero real characteristics. If there are no real characteristics, there will be no curve in the whole domain where my second order partial derivatives will be discontinuous. So suppose I have the whole domain. So if there is no line through which the partial derivatives are discontinuous, what actually that helps us? That helps us in like conveying information across any point to any other point. So if like for example, let's say about parabolic equation b square minus 4ac, this is equal to 0. So this has one real characteristic. Okay, so it has one real characteristic. What happens is like let's like take an example that will be beneficial. So let's say del t phi, this is equal to some alpha del square phi del x square. So this is a very like common equation in our transport phenomena. This is also known as the conduction equation. So if phi is temperature and I have some temperature at some like point, this will like describe how my temperature changes with time and like spatially. So what will happen? This will have some boundary conditions associated with it. So it will have some boundary condition with respect to space, the x boundary conditions, and it will have some boundary condition with time. So so at t is equal to let's say t0, phi will be equal to 0. And let's say this is a rod. So this is a rod, and at like At one end of the rod, phi is equal to 1, and the other end of the rod, phi is equal to 0. So these two will be the boundary conditions. Okay. So like phi is at x is equal to 0, maybe phi is equal to 1, at x is equal to L, the phi is 0. And like if we solve this equation, we will see that for t less than t0, the information will not be carried forward to t greater than 0, t0. Why? T equal to t0, I have already specified phi is equal to 0. So what actually happens is this t is equal to t0. This is a straight line, and if you solve the for the characteristics using the formula that we have already discussed, like in the previous equation, like here we have already discussed the formula, right, to calculate the characteristic. You will see the characteristic turns out to be of this form: t is equal to a constant, and like this is basically what it is saying. At like t greater than 0 will have the information of t equal to t0, but will not have any information from the t less than t0. Okay, is that clear? Is what I'm saying, is that clear to you? So if I draw a domain,
Hello.
yes, please.
Sir, the part, is it the meaning is like when the time is t, which is
I couldn't hear
less.
you. Could you speak again?
Hello.
Yes, please.
Is it clear, sir?
Yes, please.
Okay. So when time is less than t naught or t0,
Yes,
so that we don't consider in the calculations.
yes,
Is it something like that?
yes. We are not bothered about it, right? What we actually want to know is after T0, correct? What is happening?
Okay. So
Hmm.
we are actually analyzing the solution in the case when the time is increasing. You mean?
Yes. Hmm.
Okay.
Hmm.
Right,
To
sir.
be clear, like T less than 0, T less than T0 might also have a solution. Hmm. But that solution does not interfere with the solution T greater than T0.
Understood, sir. Thank you.
Hmm. Okay. So basically, what is happening if I draw a domain, and let's say this line is t is equal to 0, and this line is some like x is equal to 0 maybe. So t is equal to t0. Okay. Yeah, t is equal to t0 basically. Hmm. So this portion is what we are interested in. So there is a line which separates the domain, divides the domain into these two different parts, and this particular line is nothing but the characteristic. So this is the real characteristic. That we are calculating using the concept that we have discussed. Okay. However, in elliptic equation, no such case is there. So elliptic equation, one example is the diffusion equation, like the main diffusion equation. Uh, that is a elliptic equation. Let's say del square phi del x square plus del square phi del y square. This is equal to 0, or maybe this is equal to some constant. So for some like heat generation kind of. Hmm. So, but like, what is the solution of this? Like, what will be the boundary condition? There are generally, like, let's say if it is a rectangular plate, at all the boundaries, some phi value is given. Phi value for all boundaries are given, and I will have a solution in the whole domain. Now here, like whatever is the like boundary condition that affects all domain, the whole domain. Hmm. There is no input like which like there is no curve as such which separates the domain into two halves, where one the information of one half does not get carried over to the other half. The information travels the whole domain. That is the main difference between the elliptic equation and the parabolic equation. and that is why the characteristic is important. Characteristics uh, help us identify this kind of properties, and thus we can understand the equation better and thus solve it better. Okay, so there is another type which is hyperbolic. So b square minus 4ac, this is greater than 0. In this case, how many characteristics will we have? We will have two real characteristics. Character And very popular example of this is the wave equation. This is equal to 1 by sorry, c square. This is not 1. This is basically the velocity of the wave. C square del square phi del x. So if we solve this here, like if I compare it with the generic equation that we had first mentioned, a phi x plus b phi xy plus c phi yy, this is equal to some function. If I compare it with this, I can easily see that my a is 1, b is 0, and c is minus c square. Right? So my b square minus 4ac, if I like calculate, this will be b square minus 4ac will be 4c square. Okay, which is greater than 0. And I can also plot my characteristics. So dy dx, this is equal to, so minus b is basically 0, plus minus I have b square again 0 square, and this is 4c square by 2. So this is nothing but c. So y is equal to cx plus some term, like some constant. So let's say k. Okay, some constant is there. Oh, sorry,
Sir,
this is
please
not this.
explain this equation, sir. Sir,
Sorry,
dou square by dou t square is equal to c square dou square by dou x square. Which one constant, sir, here?
this is t. I'm sorry. Yes, can you speak again? Your voice was cutting.
Yes, sir. Dou square t by dou square by dou t square is
Yes,
equal to c square dou square. So which one constant, sir, here?
yes, c is constant. Yes, c is the coefficient.
So
Okay,
how will form the general equation? How will form the general equation, sir?
I did not understand.
General equation, sir.
Can you
General
type it?
equation, how will make, sir? General equation. No, sir.
Oh,
General how
okay.
will make, sir?
You can
How do
simply
you
take.
know is it one is sir?
I think there is some
A is equal to
problem
1,
with
B is
your
equal to 2,
connection.
C is
Can
equal
you
to
type it
1.
out?
Hello.
Yes, yes, please.
Sir, uh, sir, I can see in this equation, wave equation,
Yes.
where gamma square pi by dt square is equal to c square,
Hmm.
gamma square pi by dx square is written.
Hmm.
And if we go back to the generic form equation, capital A phi xx plus b phi xy plus c phi yy.
Yes.
So, and in this case, we have considered gamma square phi by dt square, and its constant is capital A, particularly if we see.
Hmm.
So, is it always necessary that we should start this with phi xx, or this is also accepted where we are
No.
considering
Yes.
gamma
Yes.
square phi?
You can take, let's say here you can take this as means I actually have taken this as my first variable t here and x as my second variable. You can take the otherwise as well, no problem.
Thank you.
Hmm. So there is no problem. In fact, I have written here like this. I have written wrong because this will be dx dt. Hmm. This will be dx dt, and this will be x is ct plus k. Okay. Hmm.
Right.
Yeah. So for the moment, let's consider a case where this k is 0. Okay. So if I like take such a case, uh, sorry, I don't know what happened. Yeah. Uh, so if I take make
So
a domain.
how do you know, sir, A is equal to 1, B is equal to 0, C is equal to minus C square, sir? A is equal to 1, B is equal to 0, C is equal to minus C square, sir. How do you know, sir, this one?
Okay. Uh, so your question is how do I compare this with the my generic form, right?
Yes, yes, yes.
So you can simply like rewrite this. This uh, take this side. Okay.
Okay, okay.
Yes. So if you take t as your first variable, then your a is 1, b is 0, c is minus c square. And like as someone else was asking, you can also take x as your first variable. If you take x as your first variable, what will happen? Your a will become minus c square. Your b will become 0. Your c will become 1. You will get the exact same answer. Your analysis will be exactly the same. It is nothing special
But
about x or any other.
but sir, first term dou square 5 by dou t square, then with that constant dou square 5 by dou x square, that is a different term, no, sir? Dou square 5 by dou t square
Yes,
is different from dou square 5 by dou x square, sir.
yes, but the difference will be compensated when you like find the characteristic. Mhm. This will change. This form will change. dx dt will become dt dx if you do the opposite one. If you take x as your first variable, then this will become dt dx, and you will also get a different solution. Hmm. So that's how it will be
Okay, sir.
compensated,
Thank you.
whichever way you do. All right.
Thank you, sir.
Yes. Yeah. So if like let's say this is my domain, so t is equal to 0, and let's say this is x is equal to 0. So here, like what are my like two curves? This is this, and this is this. Hmm. So the slopes here are given as plus c and minus c. So this is basically and like some disturbance is created, and there is a velocity c at which this disturbance is propagating. So if you take at some t is equal to some after some time t interval, let's say t is 2 seconds or something. So by that you will till where the disturbance will be felt, it will be felt into velocity into the x, the t, whatever this is. So there is a very like specific region in which this disturbance will be felt. Okay, outside this, however, there will be no disturbance felt. All right. Hello, is that clear?
Yes, sir.
Hmm. So this is like basically this as if this equation is traveling at a finite speed. Hmm. And these are like two characteristic line which is dividing the regions into these different parts where the information can be like travel from one point to another. So like in this region, no disturbance that takes place outside this region will be felt here. Only the disturbances like inside will be felt. Hmm. And similarly, whatever is happening like inside this domain, the shaded domain, we will not have any information outside this, as if this is traveling at a finite speed. and that is the very like nature of such hyperbolic equation. So whenever we are like doing compressible flow equations, this kind of these kind of equations are very common. Okay, all right. So next we have some questions like regarding this characteristics. So let me see, first let me
Hello.
see. Yes, please.
On the same slide here, I can see the two inclined lines, red colored lines.
Yes,
These are actually characteristics, real
yes,
characteristics.
yes.
So in this, the shaded area is the disturbance created,
Yes,
propagation of disturbance.
propagation of disturbance will be confined in the shaded area. So suppose you are like making some disturbance, and like
So,
in this case, like C will let's suppose it is the like speed of the wave, speed of the disturbance. So after a certain amount of time, you will be able to like let's say the speed of the disturbance is 5 meters per second. So after 2 seconds, you will be able to feel the effect of disturbance within 10 meters, right? 5 meters per second into 2 seconds, 10 meters, you will be able to feel the disturbance. However, if you are standing at let's say the distance 20 meters from the source of disturbance, you will not be able to feel the disturbance yet. It will take more time to reach you. That is the whole concept.
right, sir. Thank you.
Okay.
So it means that when we are selecting the numerical method, it will be working in this specific zone where disturbance is created.
Yes, because
And
that's
then,
what we are interested in.
oh, right, sir. Thank you.
Hmm. Hmm. Right. So this is basically the difference between this elliptic, parabolic, and like hyperbolic equations. So I had a few problems here, but I'm like running out of time. So I think the best thing to do will be like you can like see the lectures of week one and like means uh, try to understand, and we can like solve the problems in the next class. Okay.
Sure, sir.
Hmm. All right. Thank you everyone for joining. So this session will be conducted every Tuesday. Same link. Like see you again on Tuesday, next Tuesday.
Thank you
Excuse me,
so
Thank
much
sir.
you,
for
sir.
your
Yes,
effort,
yes,
sir.
yes. Please, please, please.
Is
If you
there
have
any
any
way
doubt.
we can access the recordings of this session?
Yes. So this like all these sessions are recorded and will be uploaded in YouTube, and you will get the YouTube link, and also you will get a
Wh-
link to this
Sir,
slides.
sir, can you send through my mail, sir? Mail means I can get it.
No, like it will be coordinated by the NPTEL itself. So you will get everyone who is registered in NPTEL will get the YouTube link as well as the slides. Okay.
Okay, sir. Thank you.
Mhm. All right.
Okay, sir. Fine. Thank you.
Okay. Thank you for joining.
Thank you, sir.
Yes. I
Thank
am
you,
closing
sir.
the session.
Thank you.
All right.